Welcome, everyone. Today, I'll be talking to you about quantum dots, the epitome of nanotechnology. I'll discuss their physics and their applications, and wrap up the talk by touching on their future prospects a bit. To start, quantum dots are nanocrystals that are tens of atoms in diameter. This translates to around 2 to 10 nanometers in size. Quantum dots are sometimes called zero-dimensional objects because their size is nanoscale in all dimensions, as opposed to bulk semiconductors or even 7 to 10 nanometer transistors, which are only 7 to 10 nanometers in one dimension and they're larger in the others. Quantum dots provide great flexibility and versatility for a variety of devices and applications. The most important and relevant property to manipulate is size. Quantum dots have a band gap just like bulk semiconductors, but unlike bulk semiconductors, this band gap is incredibly sensitive to the dimensions. By reducing the size of a quantum dot, you can increase its band gap, and by increasing it, you can decrease this band gap. Along with size, we can also tune electrical, magnetic, and optical properties with other factors such as composition and the distribution of the material within the quantum dot. Because of this size and versatility, quantum dots can be used in a variety of applications, ranging from solar cells and lighting to biology. And we can use them despite their relative instability in commercial technologies such as televisions. There's room for improvement in this arena, as well as in improving quantum dot devices, reducing their toxicity, and more. But their extensive use in research and commercial technologies so far provides very promising future outlooks. So, beginning with the history of quantum dots first came about in 1980 when a Russian physicist by the name of Alexei Ekimov first made nanocrystals in a molten glass matrix. He noticed that these crystals were fluorescing and he published his results. 2 years later, another Russian physicist by the name of Alexander Efros first published a theory explaining this behavior in terms of electron confinement. A year later, Louis Bruss at Bell Labs produced cadmium selenide nanocrystals that were suspended in a liquid instead of a glass matrix. This made them easier to handle. From there, however, progress was slower. It took 10 years after that before we were able to achieve quantum dot synthesis with relative control of size, less than 5% in variation. In 1993, Mungi Bawendi achieved this milestone, which was very crucial in order to tune one of the key properties of quantum dots and achieve the fluorescing wavelength that was desired, as opposed to just whatever was synthesized. After that, progress was a bit quicker. 3 years later, the first modern quantum dot structure, which involves a core surrounded by a shell, was synthesized. And after that, there were some unique shapes, such as rod shaped quantum dots and quantum dot sheets, that were synthesized since then. The physics of quantum dots can be thought of in terms of topics that are covered in undergraduate physics classes. And we start by thinking about an infinite particle in a box, which has a certain constant potential between a given length, which we'll call L, and an infinite potential barrier outside of this region, which forces the particle to stay within this box. And Schrodinger's equation, if we solve it, tells us that not only is the atom going to be confined in this box, but that it's only allowed to have certain energies. And the energies are given by this expression here. And this figure illustrates the energies that are allowed for an atom inside a particle in a box. And so we see that for higher n, we have higher energies. Now, real-world quantum dots are not quite this ideal, but they can be modeled as corrections to the infinite well. The infinite well has what are called orthogonal wave functions. So this means that a real-world quantum dots wave function can be modeled as corrections to the infinite well. And we find that the infinite well happens to be a convenient basis to work in. And by doing so, we can also model the energies as corrections to the infinite well, which is very convenient because, as we see here, the infinite well energies are quite straightforward. Now, we have a basic core shell structure for a quantum dot, but oftentimes that doesn't suffice for real applications. This is because quantum dots exhibit what's known as Auger recombination. If charge carriers are allowed to go to the surface, then instead of emitting a photon when electrons and holes recombine, as shown here, when they basically come back together, the extra energy is transferred to another charge carrier, and this gets excited instead of a photon being released. This reduces the luminescence efficiency for a photon and for a quantum dot in trying to emit photons, and this does not give us ideal results, especially given that some applications require 100% quantum dot efficiency. There's some workarounds for that. The most important workaround is a heterojunction for electron confinement. If you look on the left and the right here, then on the right we have a low bandgap material surrounded by a higher bandgap material, and this higher bandgap provides a barrier for charge carriers in this lower bandgap material. Electrons in the conduction band and holes in the valence band would have to jump over this barrier in order to be able to travel into this material, and this requires absorption of energy, which makes the job harder. And so if we have a core with a lower band gap and a shell with a higher band gap, then it prevents the electrons and holes from going to the surface. We can also limit electron and hole motion to the surface by using a thick shell or by modifying the heterojunction such that we have multiple shells, each with gradually increasing band gap. Now, in addition to size, there might be other properties that we might want to tune, because manipulating size can produce issues with superlattices, different nanotechnologies, and also with biological marker labeling. And so one property that can be tuned could be composition, and we can adjust the fraction of different elements in an alloy, and this can actually affect the effective mass. And so if we go back to this equation here, we saw that not only did the energy depend on the length, the dimension of the box, but also on the mass of the electron. And inside materials, electrons behave as if they have different mass from free space. And we also see that adjusting the alloy composition messes with this mass. Interestingly enough, it's possible to get a lower electron mass with an alloy than one might get with a pure material of either type used in the alloy. And this nonlinearity is quite fascinating and provides us additional freedom and flexibility and interesting properties to work with. Another thing that one can manipulate could be the homogeneity of the dot. In the structure shown here, we have a very neat core shell structure, but we could also have a more gradual gradient of the material, or we could have a homogeneous dot if we wanted. And so that homogeneity could also affect the charge transport properties and band gap and whatnot. Quantum dots are synthesized in methods that fall into one of two broad categories: top down and bottom up. Top-down methods break down a bulk semiconductor into smaller pieces and involve methods such as beam lithography, reactive ion etching, chemical oxidation, and wet etching. The problem with top-down methods is that they often introduce impurities that are undesirable for the devices that we're working with. Bottom-up methods, on the other hand, build quantum dots from the ground up using precursors. There's two main bottom-up methods that are used for quantum dot synthesis: colloidal synthesis and plasma synthesis. Colloidal synthesis involves heating up precursor solutions and then controlling the temperature and the crystallization time in order to adjust the concentration of the quantum dots as well as the size. Plasma synthesis, on the other hand, uses plasmas and involves energetic surface reactions. Quantum dots have a wide range of applications in a variety of domains, ranging from energy production to sensing and lighting to medical and biological research. Quantum dots can be used to enhance the efficiency of solar cells by absorbing light within a polymer matrix and re-emitting this light at lower wavelengths that is then redirected to a smaller solar cell. This allows the solar cell to be smaller and therefore cheaper, and it's particularly useful for solar cells made of materials such as gallium arsenide and indium phosphide, which are way more efficient than silicon, but are also more expensive. The quantum dots can also be used for sensors such as photodetectors and photodiodes. They allow for these devices to be solution processed, which makes them cheaper. And given the adjustability of quantum dot emission and absorption wavelengths, it provides a greater wavelength range within which these can operate and respond to light. Quantum dots have actually already been used for lighting applications. They are used in TVs to take and absorb blue LED light from the TV and re-emit this light at longer wavelengths so that we can obtain red and green light. This makes the TV cheaper because instead of having 3 different colored LEDs, it allows for one single color to be used, which drops down manufacturing costs. And quantum dots are more efficient than light shutters at turning on and off. And so this allows for better picture quality. There's also work being done with integrating quantum dots into organic LED TVs in order to enhance the already superior properties of organic LEDs and bring further improvement. Quantum dots have already been used in photoluminescent white LEDs, but their stability is not very good and they decay quite quickly. And so more work needs to be done in this arena before we can use them for future generation lighting products. The last application that I'll discuss here is biological applications. The quantum dots re-emit light at longer wavelengths that they absorb, and this allows for better separation of their fluorescence emission from the background. And this is particularly useful in imaging sensitive tissue. There's a wide variety of techniques ranging from chromatography to multiphoton microscopy that involve quantum dots, and their small size as well as the ability to modify their surfaces makes them excellent for labeling biological molecules. However, they are made of toxic metals, such as cadmium, oftentimes, and this limits their use for biological applications, especially in humans. And so, more work needs to be done in finding quantum dots that are made of non toxic materials so that we can actually use them within tissues. Based on everything I've discussed so far, I predict that quantum dots will have a very promising future outlook. I discussed how they could be modeled with a little more than undergraduate physics, and I also talked about the wide variety of ways in which they could be synthesized. In fact, they're already being commercially synthesized, with nanosys having received approval from the EPA to manufacture over 10,000 kilograms. And they have a wide range of applications in a variety of domains. And so they have the nice combination of being a hot topic for research, but also having reliability by being currently used in consumer technologies such as TVs. And so this positions them very well for future applications and future technologies. There are several issues that are still need to be worked out, such as toxicity, reliability, and stability. But because they're already used in commercial technologies, and given just the sheer immense flexibility that comes from their size and tunability of properties, I think that quantum dots will have a future outlook that's just as bright as their fluorescence. Thank you for listening.